In today's lecture, we are going to study chapter 4, which is called isolated footings. Just let's remember what we have took before. In chapter 3, we studied bearing capacity and settlement. In chapter 2, we studied shallow foundations. Chapter 1, types of foundation. So we studied the types of foundation. We knew every type of foundation. Then we concentrated on shallow foundations. We took general rule for what we should do to design any type of shallow foundation. Then we studied the bearing capacity. This is another topic, but from this shallow foundation, today we are going to study isolated footing. So isolated footing is one of the major types of shallow foundations. Since we have already studied shallow foundations, then we can go directly into solving a problem for isolated footings, because isolated footing is just an application for what we have studied in shallow foundations. So let's start. We have, this is the normal shape of an isolated footing. An isolated footing, it's a column resting on an RC footing, and the RC footing is resting on a PC footing. This is in plane. The only thing that we should concentrate on is this protrusion of the plain concrete around the reinforced concrete. This thickness should be this thickness X should be TPC, because if I have this distance which is equal to X and this height is equal also to X, then this cantilever is just extending. I will just show you a drawing to say what I mean here. Let's just check this. Yes, here. If I have here, this is the part that is protruding outside the reinforced concrete. If I take this cantilever very long, then it will crack, because my footing is pushing on top and the soil is pushing at the bottom, and this is not reinforced. So what will happen is that the soil will push from below and this cantilever will start to crack. So to prevent it from cracking, I just go from this point, take an angle 1 to 1, reach this point. This is the area that I can guarantee that it will not crack. Beyond this, it may crack. So to be in the safe side, I'm not putting concrete to crack. I will put it just to be outside my area with a distance. Take this distance equal to the thickness of the plain concrete. This is the only relation that you should concentrate on from this drawing. Now we go to an example. It's required to design a rectangular footing to support an RC column 30 by 80. The column's working load is 1,900 kilonewton, and the net allowable bearing capacity at the footing site is 120 kilonewton per meter square, and is giving me FCU and F yield to design the concrete section. What are the given data? He's giving me the working load of the column, 1,900. This is the column working load. We said, I just remind you that we use two types of loading: ultimate loading and working loading. Why we use both? Because we have to design based on two codes: the geotechnical code, which is using the working loads, and the reinforced concrete code, which is using the ultimate load. If both were using the same type of loading, then we would be using just one. So it is not something that it is repeated in any place. It is just here in Egypt because we have two different types of codes. Later in Egypt, when our geotechnical code uses the ultimate load, then we won't be using this two types of loading. So it is 1900. To get the ultimate, we multiply it by 1.5 to get this value. So this is the ultimate load, this is the working load. Bearing capacity of soil is given, and FSU and F yield are given. So these are the given data. Calculate the area of footing. To calculate the area of footing, I have first to decide, am I going to use plain concrete thickness to the minimum so that it is just a barrier to protect my steel and concrete from being contaminated from the soil, or I'm going to use it as a structural part of my footing? Go to this drawing. This is your PC, this here below. If you use just a minimum thickness, then ignore it. Don't, as if it is not there at all. Design the whole problem, and when you finish, just add it at the bottom. That's all. But if you are designing it as a part of your footing, then it will be the first thing that you are going to design. So this is what is the boundary between using or not using for the thickness? 20 centimeter. If this thickness TPC is less than 20 centimeter, then ignore it. If you take it more than 20 centimeter or more, then you can consider it. And really, this is better because you will have to put it. So why to put 10 centimeters of concrete and not use them? Add another 10 centimeters, make them 20. Consider it in the design. It will reduce the thickness of the reinforced concrete. So whatever you paid additionally, you will gain later. So it is better. So in my opinion, it is better to use it. Don't use it. Don't put it a very thick footing. Just use it 20, 25. 30 centimeter maximum. This is good, and it will help you in reducing the cost and working in a clean environment. It will be very good in all aspects. So first thing, we are going to choose TPC to be 30 centimeter. So it is more than 20. So it is working. So this will be my first thing I will calculate. Why? Because first thing I will calculate is the dimension of the footing. In this case, the dimension of the footing that I will calculate will be the dimension of the plain concrete. I will take the column load, divide it by the bearing capacity of the soil. It will give me an area. This area will be the area of the PC because the PC is now working. What will be in contact with the soil? The PC will be in contact with the soil. It is working, it is in contact with the soil. So the area, I divide the 1900, the working load, because I'm now a geotechnical engineer. I divide it by 120, which is the Q allowable of soil. I get 15.83. 15.83 is the required area. Chooses whatever you wish. You should get an area just more than, equal or more than 15.83. Any area will be okay. So to do this, I will have to consider two equations. The first equation is the area of PC it's called the L by the B. It should be equal to 15.83. This is my first equation. This is my first deduction. This is what I should reach. This is number one. The second, it's another thing that if we consider, it will be very good for us. What is it? Here you have A and B. These are the dimensions of the column. Suppose this is 80 and this is 30. Then the difference is 50 centimeters. The best thing for the most economic approach for the design of this footing is to take this cantilever exactly equal to this cantilever. The length is the same. In this case, you will design one time and you will use the minimum amount of steel for this footing, because the moment here is the same as the moment here. If I have a load and I distribute it evenly over few of the students, each one will carry an amount of load. But if I give somebody very high load and the other small load, then I am not economic, because I'm using something more than the other. So I will be depending, if this cantilever is longer here, it will be critical, and I will have to design the footing based on this direction, so I will get a bit thicker footing. So to get the minimum thickness of footing, take this cantilever equal to this cantilever. In this case, you are in the safe side. What does this mean? It means that LRC minus BRC, it is better to have them equal to 50 also. If B minus A is 50 centimeter, then BRC minus, then LRC minus BRC should be also equal to 50 centimeters. This is what we are going to do here. We said that the first equation is the equation of the area. Second equation, we want LPC minus BPC to be equal to the difference between the column load. Here we said that plain concrete is working. So I will start with the plain concrete. So the difference between the dimension of the plain concrete will be also 50 centimeters. So now I have two equations. I can solve these two equations. The first equation is L by B equals the area, required area. The difference between L and B is 50 centimeters. This is the second equation. The difference is the same between columns. Then in this case, I can solve these two equations to get the value of B, L and B. Solving both, then I will get LPC and BPC. What is the relation between L and B of PC and L and B of RC? Let's not confuse two things together. We have the difference between L and B is equal to the difference between the dimensions of the column. This is one thing. But what is the relation between this and this? What is the relation between LRC and LPC? What is the relation between LRC and LPC? And what is the relation between BPC and BRC?
Is it the 1-to-1 ratio?
Yes, this is the 1-to-1 ratio. It means that this distance x, we said this distance x is equal to what? This distance x should be taken which value? TPC. To have a slope of 1-to-1, it means that x should be equal to TPC. It means that the difference between these two numbers is twice x. It means it is the difference, it is 2PC. And the difference between this L and this L is also twice x, which is 2 PC. This is something else. So based on knowing B and L for the plain concrete, I can just subtract what is the thickness, 30 centimeter. 30 from this side and 30 from this side is 6 centimeter. Subtract 60 centimeters from 3.8, you get 3.2. Subtract 60 centimeters from here, you get 3.7. So you get all the dimensions now. You get the dimension of the plain concrete and the reinforced concrete. Now we shift to the other part of the design, which is design of the thickness of the footing and the reinforcement. I will go to the concrete code. Then I will use the load of the ultimate load, and I will start my design. So in this case, I take the ultimate load, I divide it now by the area of the footing. This number is not the bearing capacity of the soil, it's another thing. Why? Because the bearing capacity is not ultimate, it's allowable, and the area is not the area that was required. You remember that we required here an area of 15.83. Did we get finally an area of 15.83? No, we got something more. It may be 16, it may be 17, because I have chosen two round figures. I cannot just, if I have an area of 15.83, say that you will need, instead of 3.8, 3.7123. I'm not going to use this number. I will have to round it. It will be, say, 3.8. And here it was not, say, for 4.3. It was another number. So the area itself, the area I'm using here, is different from the area that was required for the bearing capacity. So it's a completely different number. W actual is a completely different number because the load is an ultimate load and the area is an approximated area. So I'm dividing two different things. That's why, what is the W actual? It came to be 2.40. What was the bearing capacity? I remember the bearing capacity was 120. Yes, 120. It was 120. So it is a different number. I will use this W actual as this is the actual stress now below the footing. Also here the stress is not the stress on the soil. It is the stress of the RC on the PC. So the PC can carry more. That's why this number is not just, it is not the same 120 multiplied by 1.5 to be an ultimate. No, it is not just the ultimate. It's another stress. It is the stress of the RC on the PC. So it is another number. So I now reach this. This is the actual stress below the footing. So now the footing is pushing on the plain concrete with this value. So if I want to put reinforcement, it will be based on the moment caused by this W. So what should we do? We should calculate the bending moment. We said this in the previous lecture. Usually, we should calculate the moment of a cantilever, WL squared divided by 2. L is half the length of the footing. If this footing is from here to here, the column is in the middle, then I can say this distance is 4 meters, then this cantilever is 2 meters. But I can make some reduction. What is this reduction? The critical section is the section at the edge of the column. It's not in the middle of the column. Because the column adds more stiffening to the section. It is not this section that I am afraid that it would fail. The section that is subject to fail is the section on the edge of the column. Think of it. If you have a footing and you imagine that this footing reach failure, where do you expect the failure to be? In the middle of the column, no, the column will is strong, and it will add more stiffness to the section of the footing. But at the edge of the column, I don't have a column. So this is the critical section. This critical section is subjected to the highest bending moment, and at the same time, the cross section of the section is just a footing without a column on top of it. So this is my critical section. I have to calculate here something called M1 actual. Why do I call it M1? Because in some cases I may have M2. When do I have M2, do you think? This is one case if the column is shifted, but the other case we said that it is better to have both cantilevers in the two directions equal. In this case, I will have M1 here, M2 in the other direction, but M1 is equal to M2. They are equal to each other, so I calculate only M1. But in some cases, I may have a different cantilever, then I will have to calculate both. So now I will calculate the moment at this location, so it will be W Z1 squared divided by 2. Z1 is this cantilever part of the footing. This is my calculation. This is how we calculate the Z. Of course, you can even measure it on a drawing calculation. Just the length of this cantilever, half the length of the footing minus half the length of the column. It will give you this Z. Then I calculate the moment. W L squared divided by 2. Then I calculate the D, the depth of the section. This rule is taken from the code for the reinforced concrete. How we calculate the depth of any concrete section? We have an equation, C1 root M ultimate divided by FCU divided by B. And there is a factor called C1. This factor, we can take it 5. Anyway, you use what you use in your concrete design. This is an equation that is proposed for using it here. Then I can calculate the depth. The depth means the depth of steel. I still have the cover below the steel. This is not the thickness. This is the depth of the steel. So I add 7 centimeters because in footings we use a high value for the cover, concrete cover. We take it 7 centimeters according to the Egyptian code. So we add 7 centimeters to the depth. We get the new TRC or the total TRC. This is the thickness of the RC footing. Of course, as you have seen, I never take a number like this. If you tell the site that you want a footing with a thickness 52 centimeters, 0.92, it's they will not consider it at all yet. Then I have to give them a round number. So if we then go to the nearest 5 centimeters, this is the minimum you can deal with on site. Minimum 5 centimeters. The minimum things I can say is 5 centimeters. If I have a footing 50, the next one will not be 51, it will be 55. The next one will be 60, and so on. But I cannot deal with centimeters or millimeters on site. It is better for us because your eye will not be able to judge mistakes unless you have. If I look from a distance to a footing and I know that it should be 50 centimeter and I find it 60, I will discover the problem even without measuring. But if it should be 52 and and it was constructed 53, my eye will not judge the mistake. So it is better for the contractor and for the engineer who is supervising the work. Now, I will take it to be 550. This is the T. So I have to recalculate the D. What is the relation between D and T? If you are following me. Now I added 7 centimeter for the D to get the T. And then I have to use a round number, a round figure. I use this number. How can I get again the D? Minus 7 centimeters again. Yeah, I just. So now these are my new numbers. I have now a thickness, and I have a total thickness, and I have a depth of concrete of steel. Now I have a depth of steel. I should go to design the steel to get the amount of steel, but it is better not to do it now because we have some checks to do. These checks, if unsafe, may affect the value of D and T. So it is better, instead of repeating a lot of effort, stop at this location, do your checks. If they are safe, continue based on the number you have got. If they are unsafe, increase the numbers again till you reach the safe numbers and then use it for the design of steel. Yes. So now we go to the checks. What are the checks? Now we go to the shear, what you have just asked about. You remember, first of all, I have to remind you of the difference between check shear and check punching. We have two things. We said that shear is if you have a bar of chocolate and I want to get a piece and give it to you, then I will shear using my two hands part of the bar of chocolate and I will give it to you. So shearing is cutting a piece from a bigger piece. But punching is putting the bar of chocolate on soil and then pushing with your finger on top of it till you penetrate the bar of chocolate. So this is punching. So this is they are both shear. Both are shearing stresses, but the application of the shearing stresses is different. In one case, you are separating a portion from a bigger portion, and in the other case, you are penetrating it. It's a different shape. So now we are checking shear. The critical section for the design of the thickness of the footing, when we tried to calculate the bending moment, we said that the critical section was on the edge of the column. This is the critical section for calculating the moment. For calculating the shear, this load coming from the column, it does not go vertically down. Here, this is the column. There is a load coming down from the column, but this load has some kind of dispersion. It does not go vertically down, it spreads a little bit. If there is load going down, can I shear this section at the edge of the column? No, because I'm still having load on top of it, preventing me from shearing it. So they said, in the method they propose for the design, go away about a distance of D by 2. D is the depth of the reinforced concrete section. So you just move away D by 2 and if you go d by 2 all around the column, this is the place where we can start having our shear, the critical section for shear. So here is a critical section for shear, here is another critical section for shear, and so on for the other two faces. Okay? So now we have to do the check of shear for a cantilever, for the portion here or the portion here. So we'll just calculate this amount. Check the amount of shear stresses on this section. Compare this amount of shear stresses with the allowable shear stresses that the section can carry. And for this we have an equation given by the code. The code tells me that if you have a section with a dimension, say the B and thickness of so and so and B and so and so, then the allowable will be a given value. I take this given value, compare it to the actual shearing stresses. If they are, if the shearing stresses, the actual shearing stresses are less, then it is safe. If they are more, then I have to increase the allowable. How to increase the allowable? By increasing the dimensions of the section. What can I do? I cannot change the area now, because the area is now fixed. It's related to bearing capacity and so on. I can now work with this thickness, increase it, increase this thickness. You will end up having higher allowable, so it will be safe. So that's why we said don't calculate the steel now, wait, because we may, during the check of shear, increase the D, or during the check of punching that will follow. So this is an equation. This is the actual shearing stresses, the actual shearing stresses on the section. It is the amount of load that we have. Q is the amount of load here that we have, divided by the dimension of the section that will be sheared. This is the actual shearing stresses. I will compare it with the allowable shearing stresses given by the equation of the code. I will just divide this by this and so on. I get a number. Compare both. If it is less, then it is safe in shear. I go to the other thing that I will have to check. It is the check of punching. Check of punching, I have, let's just remember the check of punching. I have, here is the column. I just go D by 2 all around, and going D by 2 all around, that this will be my section that will be punched. So now I can do the same. I will calculate the load on this section. This will be the actual load causing punching, the actual punching stress. And I compare it to the allowable punching stress, and so the same that I have done for shear. So check punching, just calculate the load. You will get a number. Of course, here it is a little bit complicated, because the area that will be sheared is not just a line, it's this square. So I have some minor complications in the design. Instead of having a line, it is a square with different sides. I have to calculate it. So this is the area that will be shear. This is the actual punching shear stress. I divide the load that will be shear, that causing shear, by the area to get this number. This number should be less than the allowable. Where is the allowable? I calculate the allowable from the equation given by the code. I substitute in this, I get a number. If this number is okay, then I continue. If it is not okay, like this case, it is unsafe. then I will have to increase the value of the thickness. So I go again, increase the value of T, recheck for punching. If it is okay, then I don't have to recheck anything again, because everything before was safe. The only thing that was unsafe was the punching. So if I now increase and the punching is safe, then everything is okay. Once everything is okay, I calculate the steel. Based on which depth? The new depth. Because here I used a different, you remember it was how much before? Here it is, now it is 650. I think before it was, when we started here we took it 550, so we increased 10 centimeters. So this 10 centimeter, we are going to use it to reduce the amount of steel. If we calculate the amount of steel based on the 55 centimeter, we would get more amount of steel here than what we've got now. Once we get the total amount of steel, here's something that you should know. Very important is how to draw a plan and elevation of a footing. This is very important for any engineer to know. You can calculate the area of steel, but how are you going to calculate the number of rebars and the distribution of these rebars and the shape of them? This is very important. So now I get this area. This area, here we took it 6,518. What is the minimum number of rebars I can use in 1 meter? By the way, this is per meter. This is a moment, this is calculated based on a moment on a meter of the footing. So 6,518 means that I have 6 rebars next to each other. If I have 1 meter divided by 6 rebars, then the spacing between rebars will be okay. I have something in the code tell me that you should not put 2 rebars away from each other more than 20 centimeters. More than 20 centimeters mean the minimum I have 5 rebars per meter. So in this case, it is 6 rebars. Okay, this is okay. Yes. So now this is the plan. This is the cross section, and this is the plan. I said that I have 6,518, so it is 6,518 for in this direction and 6,518 for the other direction. I did not calculate the other direction. Why? Because I have a cantilever from both sides equal, so I don't have to recalculate. If you are using a different cantilever, then you would have repeated the design twice. So this is now 6,518 here, 6,518 in the other direction. I use rebars with the U-shaped. I don't put top reinforcement in isolated footing. This is very important. I don't have top reinforcement in isolated footing. But what about this? What is this dotted line? This dotted line is not a rebar. It's just, we call it in Arabic, sikh tarbit. It is just a rebar to fix, to keep the U-shaped in place. Because if I put the U-shaped, they will not stand. I will just have to put a wire all around or anything all around, so that it would keep my U-shaped standing in place. So it is not, it's just one rebar phi 12. It's not designed, it is just put like this. That's why it is a dotted line. So actually I don't have any rebars on top. That's why isolated footings are very economic. I don't have to put top reinforcement. And of course I put the reinforcement of the column, not the reinforcement, just we call it in Arabic ashayr. the starters of the column. And then I put my plan. I show the column. I show the thickness, the dimension of the footing, everything, all the information I designed before. I put it in these two plan and cross section. This is very, very important to do. This ends the isolated footing. So isolated footing means that it is carrying vertical load. But footings carry more than vertical load. It may carry moment, it may carry horizontal load. So I have to check other cases. The important case that I'm going to design is the moment. If I have a vertical force and a moment, are there footings subjected to moment? Yes, of course. A moment due to wind, moment due to earthquake, moment due to frame, the legs of frames and something like this. I have moment, so it will be reflected on the footing. I have to, the footing should carry this. How to design this? I have two approaches. One approach we will take next lecture because it is it needs lots of discussion, and one is very trivial. What it is? It's called the case of permanent moment. Suppose you have moment that is always in one direction. I have a moment always in one direction. What is this one direction? How this happen? Check this frame, multi-story. It's like a building. There should be a footing here, and there should be a footing here. The moment is drawn in this direction. Can the moment be in the other side? No, because this is how we solved this frame. Moment will always be here, here, here. It's fixed. It's not changing. It is always in one direction. So in this case, I know that the moment will be in one direction. So why not make an opposite moment that would cancel the original moment, and then I don't have to design for moment? How can I do this? You remember that any force multiplied by an arm will cause a moment. If you are standing in the sea, in the middle of, on top of a square raft, this is a wooden raft on the, and you are just on top of it. If you move to the right or to the left, you're going to fall. Why? Because you will induce moment on this raft, and the moment will let you fall. Because when you were standing in the middle of this wooden raft, then in this case you don't have moment, just normal force on this wooden plate, nothing will happen. If you move to the right or move to the left, then in this case you will add moment, because your weight will be multiplied by the distance between your CG and the CG of the raft or the plate where you are standing, and you will cause an additional moment. So why not, if I have moment here, I take this moment, divide it by the normal force I have from the column. Suppose I have from the column a normal force. Yani this frame has two things. It has a moment here, and of course it has a normal force. Take this moment, divide it by the normal force, you will get an eccentricity, a value of a distance. If you manage to shift the column in a direction opposite to the moment, so you will induce another moment that is equal to the original moment, but opposite in direction. You understood what I mean? خلينا نشوف الرسمة دي. Let's look at this drawing. This is a column. and this is a footing. The column should have been in the middle. What happened? We shifted the column here. By shifting the column here, this column caused additional moment on this footing. What is the value of this additional moment? The value of the P, which is the load of this column, multiplied by a horizontal distance, which is the distance from here to there. This is additional moment that I have induced. If this footing was subjected to a moment in the opposite direction, then they will both cancel each other. So this is what we do. We take the moment that is already on this footing is subjected, say, to a moment in this direction. There is a moment that wants to overturn this footing or to rotate this footing in this direction. What is the value of moment? It is m. And I have a normal force here, n. If I divide m by n, and I take this column, instead of being in the middle, shifted by the value of the eccentricity E, which is m by n, then the value of the resulting moment on this footing will be equal to what? 0. Because you managed to vanish the moment. So this is the first case. But this case can only be applied in case I have fixed moment. I cannot apply it to moment coming from the wind, because today the wind is from here, next day the wind is from the opposite direction. Then in one case it will be in favor, and in one case it will be a catastrophe, because I will have double the moment. Instead of having, in one case I will have 0 moment, and in the other case I will have double the moment. So I cannot do it. If I have variable moment, changing the direction, then the best thing is keep the column in the middle and design the footing to carry a moment. This is what we will study next lecture. But in this lecture, all what we have to do is that this is the case, as I told you, if I have variable moment, then in this case I have to design a footing to carry variable stress due to moment. I cannot just shift the column. But in case of permanent moment, this is an example. We are going to just say it in few words, and we will repeat it next time as an introduction to the variable moment when we come. But here it is the case of the permanent moment. Everything is given like the previous example, except that I have moment in addition to the normal force, and this moment is permanent, it is fixed in direction. So the first thing we have to, it's the same, all the same. The only difference I will have to do is to divide, where is the, just a moment, here it is, the same procedure. The only difference is that I will add something. I will divide m by n. Once I divide m by n, I will end by having E. E is the eccentricity. The eccentricity, if I shift the column 0.42 meter in the opposite direction of the moment, I will cancel the moment. That's all. The same will happen. But I need somebody here to be very clever and tell me, there is another thing that differs. Of course, now the moment is cancelled. But what about the cantilevers? They are not the same. Because I shifted, I was forced to shift the column, then in this case, I did not have equal cantilevers from all sides. So in this will be similar to another problem where I have different values of cantilevers. I have to study this moment, and I have to study the other moment, and I will design the footing based on the bigger moment, and will get the value of steel of the other direction based on the other moment. You got me with this? This is the only difference. This is exactly what we will discuss next time, but I will just to know that in case of permanent moment, it is similar to the normal case, but I will just shift the column by a value of E, which is the eccentricity. The only difference is that I will have different cantilevers because the column is shifted. In this case, I will have to design both directions, not one direction as the other one. We can stop in this part of the lecture, and next time we will continue checking this example step by step and going into the case of the variable moment where we have different method for design. Thank you and see you next time.